Hey everyone, Professor Hank here. So today we're going to talk about doubly linked lists. We'll talk about some of the use cases for them. We will talk about algorithms for interacting with them, and we'll also do some analysis on the performance of those algorithms. So let's go ahead and get started. Now let's recall that with a regular old linked list, we've got a node that we can define as something like this. If we were in Java, we might do something like this. We might do class node, and we could have some data that we're storing, call it X, and then we would have some self-referencing pointers. So we'd have something like node next, right? Now with a doubly linked list, what we're going to do is we're going to add another reference. In addition to the next reference, we're also going to have a prev reference. Now what this means is that our node is going to have potentially, in addition to a node that follows it, such as you would have with a singular linked list, you also can have a node that precedes it that it knows about. So we've got two references. And so this allows us to do traversal in two separate directions. So our picture gets a little bit more complex, right? So this is a doubly linked list. Whereas with a singularly linked list, you can only go in the one direction. You've only got the next pointer, which allows for only traversal in one direction. So this is a singly linked list. So if we were to define this in Java, then we'd have something that looks like this. If we were to do it in C++, then we could have, then it would look something like this, class node, maybe something like this. Or we'd have two pointers instead. So next pointer and a prev pointer. And then if we were doing Python, then we might have something that looks like this, where we would have our initializer, which would have the self reference. And then we would create our class variables. So self.x, then we initialize it to 0. Then we would have self.next equals none. And then we'd have self.prev equals none, right? So Python, Java, C++. Big difference, we have a next reference or pointer or variable, and we have a prev reference pointer variable. Now, what are some use cases for this? You can imagine where this could be useful in the case of, say, web browsers. You can think about when you're hitting the forward and back button, moving between pages. Another potential use case would be, say, a music player where you're able to move forward and backwards from song to song. And, if you wanted to hear the same song that just played before, easily traversing in two directions. So let's develop our first algorithm for this. And this is going to be the append algorithm. And the append algorithm is going to be a bit different than a regular linked list. So for our implementation of this data structure, we're going to have both a head reference. We're also going to add a tail reference. And then we're just going to be storing integers inside this thing, just to keep it simple. So head reference is going to maintain the memory address of the first node in our doubly linked list. The tail reference is going to maintain the memory address for the last node in our doubly linked list. And so we need to have both of those in scope for our algorithm. And then, of course, the value that we're going to be adding to it. Now, just like a linked list, a singularly linked list, if the head reference is null, then it is empty. So that would be a picture that looks like this. But we also have got that tail reference. So when the list is empty, we're going to have to keep it referring to null as well. And then as we're adding nodes, not only will we potentially have to update this head reference, but the tail reference as well. So let's go ahead and flesh out this algorithm. So we're going to start off by creating our node. So we'll create a temporary variable and we'll assign to it our new node. And so when we do that, that is going to give us a picture that looks like this, where we've got this temporary reference holding on to it. And then we're going to have to store the value that we want in that node, value or values if you were doing something more complicated. And then we have to set the next and the prev to null. Next and the prev reference to null. So then our picture kind of looks like this. Okay. So whatever value is inside that node. Now, two possibilities here. Either our list is empty or it's not. Right, so we've got that first scenario here. So let's examine that. Now, how can we tell if we have an empty list? Well, we just have to look and see if the head reference or the tail reference, we could check either one because our list is defined as being empty if those are pointing to null. So we could check either of them. So what I'll do is I'll just check the head reference because this is similar to what we do with a singly linked list. So if the head reference is set to null, then what I have to do is I have to set the head reference to my new node, and I have to set the tail reference to my new node. So when I do that, then my picture here in scenario 1 changes. So they're no longer pointing at null, they are pointing to what n is pointing at. So we're copying the contents of our n reference into t, into our tail reference, and we're copying it into our head reference. So now our picture turns into that. Now we have to double check to make sure all of our links are good. So the head reference points to a node, the tail reference points to a node, both the next and prev of our node are pointing to null, and so we're good. We're good to go in that scenario, so we handle it just fine. Now, what if we then decided to add another node? So what are we going to do? Let's go through our algorithm and flesh it out. We create our new node and we assign to it a new value. So we'll call it value sub 1. So we set its next to null and we set its prev to null. Now, is the head reference set to null? No, because it's got the memory address of our v node in it, right? So we're not going to do this. We need to do something else. So what are we going to do? All right, so what we can do is we can take advantage of this tail reference here. We don't have to have a loop to find the last node in our list. We already know where that node is. And we know that because its memory address is in our tail reference. So what we're going to do is we have to update our tail node's next reference. So update tail next. We have to update our new node's prev because we want it to point to the node that the tail is referring to. So we're going to update n.prev. And then finally, we have to update the tail reference itself. So let's do that and let's make sure that everything works. So t next is set to n. Prev has to have the memory address of the last node in the list. And it's the last node if it's the tail node. It's the tail node because the tail reference contains the memory address of the node. So we're going to have n.prev set to t. And then finally, we're going to have our tail reference updated to the new node. So we're going to do t set to n. Now let's update our references. So t next set to n. So t next set to n. So we're going to overwrite contents of this reference with the contents of this reference. And so this is now going to refer to that node. And we have to do n.prev set to t. So our prev set to t. So we're going to write into this reference the contents of t. Now what's in t? The memory address of the last node. So our picture changes to this. And then finally, we're going to update the contents of our t reference with the contents of our n reference. So we're going to take the contents of n, which is the memory address of the v1 node, and write it into t here. So that is going to change our picture to this. All right. So once the algorithm's finished, this is just a local temporary reference. So it's going to go away. Now, does our list maintain all of its links? We start at the head reference. We follow the links to the v node. Then we use its next to go to the v1 node. And the v1 node's next goes to null. And that's correct because the last node in the list has its next point to null. Now, can we traverse in the opposite direction? We start off with the tail reference, which is referring to the tail node, which is v1. We follow its prev reference back to the v node, and then we check the v node's prev, and that points to null. So we're totally fine. So that all looks really good. So let's just do one more to make sure that our append is working. And then we'll do some analysis on the append. So let's say that I'm going to add a new node. So we're going to start right there. So got our new node. We assign its memory address to our n reference. It's been assigned a value. So we'll call that v sub 2. Its next is set to null. Its prev is set to null. And then we check the head reference. So is the head reference pointing to null? No, it's pointing to the head node. So we skip down to the else and we set t next to n. So tail next, that's this right here. We're going to overwrite with the contents of our n reference. So when we do that, the tail node is no longer pointing to null. It's now pointing to our new node, our v sub 2 node. and then we do nprev. We override its contents with the contents of t. So it's no longer going to be pointing to null. It's now going to be pointing to the tail node because the tail node's memory address is in the t reference, the tail reference. And then finally, we overwrite the contents of our t reference with the contents of our temporary n reference. And what is our temporary n reference pointing to or referring to? Our v sub 2 node. So our picture changes to that. Once the algorithm's over, the n reference goes away because it was a temporary local reference. And now we can check to see if our links maintain. So we start off with the head reference pointing here, and then we can follow its next to the v1, and then we can follow v1's next to v2, follow v2's next to null. That's exactly what we need to have happen. So that is fine in that direction. Now we'll move in the opposite direction. So we start off with our t reference, which is pointing to the tail node, and then we're going to follow the tail node's prev, our v sub 2 node prev, to the previous node. The v1 will follow its prev reference, the previous node, the v node. So that's good. And then we will use the prev reference in our v node, which goes to null. So we've maintained our links. The important thing when dealing with reference or pointer-based data structures is that you maintain all of those links. So that way you don't end up with any reference or pointer or variable that's pointing to an invalid memory location. So now let's do some analysis on this algorithm here. So you'll notice that there's no loops here. That is fantastic. That's a good indicator or hint that you're not going to be in linear time. So how many operations do we have? Well, we've got our new node creation. We've got the assigning of v, so that's 1. We've got 2. Then we set next and prev to null, so that's 3 and 4. We have a test here, so that's 5. Now in the worst case, we don't have an empty list, so we have to kick down to the else, which gives us 3 more operations. So that's a total of 1, 2, 3, 4, 5, 6, 7, 8 operations in the worst case. So that's big O of 8, which is constant time, which we can write as big O of 1. So this is a constant time algorithm, and it's very efficient because we don't have a loop. It doesn't matter how big the list is. It can have 100 nodes or it could have 1,000 nodes, and we're still only ever going to need 8 operations. So it's big O of 1. It is a constant time algorithm.